In week 3, we're going to cover the basics of machine learning and look at some simple models, including linear regression. So remember that we're trying to create a function f hat. The hat means that we're estimating what happens in the real world. So we can't capture the real world exactly, but we want to create as good of an estimate as we can. And so there's two ways we can do this. One would be to have a mechanistic understanding. We want to know the internals of how things actually work, and we can exactly know the answer. So this really only happens to be the case in mathematics, logic, a few other fields. In the real world, there's a lot of non-deterministic things, so we can't do that. So we have to take a more behavioral approach, meaning that we're going to observe something, capture some data, and then use some statistical analysis in our model to try to capture what happens when you put in some inputs, what will the answer be? And we kind of iterate back and forth between creating different theories, trying different models, adding more data, etc. As we've said before, machine learning models are mostly math. So they are learning the probability distributions. Again, remember causation versus correlation. This is based on correlations that we see in the data. So you want to gather your data and then go through this train and test cycle. You're going to repeat that. You may try different types of models, different types of hyperparameters. So a hyperparameter is something that the engineer sets in clustering. You're going to choose how many different clusters you want, for example. There's a number of different hyperparameters based on what actual algorithm you're using. And then there are just the regular parameters, and those are going to be learned by the model through training. Then finally, once you get a model that is accurate enough for your use case, then you're going to deploy that, put it into production. So let's say we're going to create a classification system that's going to try to detect whether a given email is spam or not. In supervised learning, which we have, we're going to base it on this tabular type of data. We talked about that before. And in this case, we have the two data points. We have for an email, the number of spam keywords, so words that are typically associated with spam. Let's say we have a list of those, and then how many links and attachments that are in the email. So those are our two pieces of data. And this model, I should say, this tabular data structure ends up being used all throughout computer science. You can see some examples here. So relational databases, this is essentially a database table. When you go into object-oriented programming, an object is like a template that is an instance of the email, and it has those attributes there. And then oftentimes when we talk about machine learning, we're going to think of this in terms of a feature vector, which means translating each of these attributes into a numeric form. In our case, they're already numbers, and putting those into a matrix, or really sets of vectors, and then that will be the input to our model. We're going to talk in this video about how we consider the geometric view of that, which really is going to intuitively help us understand what these models are actually doing. So our data set, we're going to think of it as an n by d matrix. So in this case, in computer graphics, you usually do it the other way around. You do the x coordinate, then the y coordinate. But in data science and machine learning, it's the row numbers first. So we have an n by d matrix. So here we have 3 email samples. So n equals 3. And we also have 3 attributes. Now 2 happen to be our input features, what we're going to try to use to predict our target, which is whether it's spam or not. So in this case, we've got three samples. 1 is actually spam. And remember that a key assumption is that this IID. So all of our samples, our instances, they're independent, meaning one didn't depend on the other, or any other one. And they're identically distributed, which is a fancy way of saying basically they're drawn from the same distribution. And so that lets us assume that if we have an idea of what the probability distribution of the whole set looks like, then they would all apply to that. And so we're going to take this sample and hope that it's representative enough, and then use that as the distribution for all emails that we could possibly see. And that's how we'll be able to predict whether the email is spam or not. Now, this is a really important distinction. So we have these numbers, numeric data here. Obviously, we can look at it from the numeric perspective. Remember that we looked at normal distribution. There are 2 main pieces of information about normal distribution, which I have here. That would be your average or mean, where the center of the data essentially lies, and then standard deviation, roughly how spread apart are the values. So you can see that. Now, the other way to consider it, and it's very helpful in machine learning, is to consider the geometric view. So each of these pieces of data, we have 2 dimensions, so we can look at it in a 2-dimensional graph, and think of those 2 numbers as a point in this XY, or 2-dimensional coordinate space. So this diagram on the right here, you can see I've plotted each of those points. Now, remember that email 2 is actually the one that is spam. And so if you look on this graph, you can see that geographically, or from a distance perspective, these two that are closer here are not spam, and in the upper right corner, that is the spam. So the reason that it helps to consider the geometry view of our data is because distance is going to be similarity. If two data points are closer in the geometric space, that means they're more similar. If they're farther apart, they're less similar. So we're going to talk more about that. This is a really important point. Okay, so why do we even bother with the geometric view? So we talked about the similarity and distance. So what is that? How does that help us? So in clustering, if I have a lot of data points that are really close together, that would be, we can consider that a cluster. And if you think about customer segmentation, that's just one use case, a very common one where I may not know everything about my business's customers, but if I have a number of data points about them and I see different groups, then maybe each of those groups or clusters has different purchasing patterns, may respond to an advertising or a promotional offer differently. Without even knowing anything else, I can just look at the clustering. Another use case for this distance or similarity is anomaly detection. So if typically most of my data points fall within a certain range in the geometric space and I start to see some that fall outside of that, then I can say, okay, well, something's going wrong here. So this is used in monitoring systems, could be like video surveillance, other types of systems like that where I'm looking for something outside of the norm. And what is normal? Well, where my points lie in the geometric space is one good measure of that. Now, when we talk about distance, what are we actually talking about? Well, here are two main examples. So in our two-dimensional space, it's again easy to view this. Everything I'm talking about, by the way, we're looking at some simple cases, but when you get into 3 dimensions, 4, 5, 10, 100, all of the same principles are going to apply. Spare one we'll get into, but you can't, other than, or rather I should say larger than 3 dimensions, you can't visualize it, at least not easily at all. And so that's why we talk about these things in a few dimensions. But usually machine learning models have many more features than just 2. But this is why we're doing this. So the L1 or Manhattan distance is this green line here. So what is that? It's called Manhattan distance because think about driving through New York City downtown. You can't obviously drive a straight point from point A to point B because there are buildings in the way. You have to go and navigate on the city blocks versus Euclidean distance, which is the straight line distance. So oftentimes you'll see Euclidean distance used, but these would be L1 and L2 if you're norms, if you hear about that in the literature. So just briefly, how do we actually calculate this? Now don't get alarmed. I am going to show you little bits of math here. It's machine learning, like I said, they're mathematical models, so you can't get completely away from it. But I kind of want to show these a bit so that you don't get alarmed by them. They're really not that bad. So what is this formula here saying? The epsilon, or kind of big Greek letter E there, is saying for all of my data points, and I can index them by the letter I. So from 1 to n. Remember that we have n samples in our data set, right? For us, it's actually... well, our email set has 3, but here we're just considering these 2 points. So we have 2 points and we're going to take the absolute value of the difference between the 2 coordinates. So on the x-axis, 3 minus 1, we get 2. And on the y-axis, going up and down, 2 minus 1 is 1. So 2 plus 1. So your Manhattan distance is 3. Now, if we had reversed the order of the points because we're taking absolute value, this would come out to be the same. And that is actually the reason the absolute value is in the formula. So real easy, that's the Manhattan distance. Okay, now the Euclidean distance. So where does this come from? This actually comes, if you remember the Pythagorean theorem back in school, to figure out the other side of a right-angled triangle, a squared plus b squared equals c squared. That's all this is. So in this formula here, we're just adding up the a squared plus b squared. So the square of the difference of our x and y coordinates. And then because equals c squared, we have to take the square root in order to actually find out what c is. So here again, you can see, so 2 and 1 are our distances. When you square those on the bottom, you get 4 plus 1 is 5, so square root of 5. So our Euclidean distance, the straight line distance here, is approximately 2.236. Okay, great. So now that gives us, that's a relative measure, right? That distance by itself doesn't tell us necessarily anything, but when we look at the relative distance of other data points, that will inform us a lot more. Now, something that we haven't talked about a whole lot yet is when you get into many, many dimensions, you get what's called the curse of dimensionality. So the Euclidean distance ends up having less of a meaning. Why is that the case? You can think about if you just take a two-dimensional square and then you add a third dimension like a Rubik's Cube. If you consider the distance from one corner to the other, just by adding that third dimension, the distance from one corner to the opposite corner, it grew only because we added a single dimension. And this continues to get worse and worse and worse. So when you get into high dimensional data, typically we wouldn't use Euclidean distance, we would use a different measure, and that's cosine similarity here. So remember, we're in a high dimensional space and our data points can be thought of as vectors from the origin, like 0, 0, 0, however many dimensions you are, pointing to some point in that space. And so you're looking at what's the angle between them. And that is your cosine similarity, you can see as it's represented here. Now, the cosine similarity is a value between 1 and -1, and that actually tells you a lot about your two feature vectors. So in this diagram along the top, you can see on the left-hand side here, you've got two feature vectors that are mostly pointed in the same direction. So their cosine similarity is going to be close to 1, and that means they are semantically very similar. Compared to this middle point here, where if you've got two feature vectors that are pointed at a right angle or orthogonal to each other, your cosine similarity would be around 0, and there's no relationship between those. The concepts related there, not much to say one about the other. And then you have all the way going close to -1, which would be the feature vectors pointed in the opposite direction, and that would be their opposite, closer to their opposites of each other, so hot and cold. Something like that. The way you actually calculate this, and you don't need to know this specifically for this class, but it is the dot product of the angles divided by the norm of A times the norm of B. You can see the math here down below for these two data points that we've been looking at. You end up with 0.95, which again is close to 1, which means from a cosine similarity perspective, those two data points we were looking at are very similar, very closely related. Briefly, here's an example of an orthogonal one where the cosine similarity ends up being -0.14, so pretty close to 0. So in this case, those two feature vectors really are not related to each other. Okay, so now let's talk about, we have this geometric view of the data, and we want a model that's going to help us fit that data really well. So let's say we have these 4 data points here, and they're just arbitrary data points. Doesn't matter what they are, you have two features, X and Y. So the blue line is what a linear regression model tries to do. We're going to talk about that in just a second. It basically tries to draw a straight line, hence the linear, and as closely as possible fit those data points as well as it possibly could. The red line is more of a cubic model or nonlinear model, and you can see it's fitting those data points exactly and thinking based on the curvature where they're going to end up going. So those are two different models that you could use to represent this. Now, obviously, 4 data points is not a lot, but for the purpose of illustration, these are two types of models that, in this case, the cubic model fits your test data perfectly. It fits your training data perfectly. Whereas the linear regression model, you have a little bit of error. Each data point is some small distance away from your blue line, which is your predicted line. Now, remember, your goal is not just to minimize your error on the data that you train on. You want to minimize the error when you actually go use the model in the real world. And so that's what we would call test time. So you can see I've now shown these other 2 data points that we didn't have at training time, but now we have when we're using our model to make predictions, the 10.4 and 12.5. So now you can see that even though the cubic model, the red line, fit our training data perfectly, it's going to do a very bad job of running inference on those 2 other data points, whereas our linear regression model is going to do pretty well. It's still going to have that small error, but it's going to be much better at predicting the unseen data points. Here's the actual formula for a linear regression model. And I'm showing you the math again, not so that you get alarmed or scared off by looking at this, but rather the opposite, so that you realize that these things aren't so scary. You know, I used to be like, when I saw this stuff, my eyes would kind of glaze over, but it's not that bad once you unpack it. Remember that you can read one sentence, you can read very quickly, but one formula math formula, there's a lot of information very densely packed into it. So it's going to take longer. So just, be patient when you do this. But what this says is y is our target. That's what we're trying to predict. And remember how we represented our function, our model as a function f of x. So x, capital X, we have some number of inputs. That's represented here by some arbitrary number, x1, x2, all the way to xn. Remember our n by d matrix, we have n input samples. The value for each input is multiplied by a corresponding beta. So x1, input x1 is multiplied by beta 1. Input x2 multiplied by beta 2. So beta 1, 2 to n, those are weights or coefficients, and from a mathematical perspective, what does the weight or coefficient mean? It's saying how important is this variable to our end prediction. A high positive value would be it's very important and it increases. A negative value would mean it actually detracts or reduces what our estimate is going to be. So to put this in practical terms, let's say our model is to estimate the sales price of a house. And so one of the features would be number of bedrooms. So for each additional bedroom that the house has, you might see a larger increase in value. Whereas if you added another 50 square feet to the square footage of the house, okay, it marginally goes up a little bit, but not as much as having a whole extra room. And then maybe there are some features which actually would detract or bring the price down. Let's say it's adjacent to, not the entrance or exit to a highway, but it's just adjacent to an interstate, and so you get a lot of traffic noise. Maybe that is a negative, it brings the price down. And then finally, this beta 0 is our bias. So that would be a starting point. And you can think of this as, say, for this sales price of a home, let's say, even if it's a really small, like a studio, small square footage, really no bedrooms, there's one big room, the house is not going to sell for $0. There's always going to be some minimum floor starting point price just for any piece of real estate. And so you can think of that as that's what your bias or beta 0 is going to be. So I wanted to show you some Python code to run the linear regression model. And I've taken the data here that is just those arbitrary data points we're looking at with the cubic model and the linear regression model. I've put those into an array here, and then pandas is a library that's often used in Python for machine learning. So a data frame is essentially like our n by d matrix. It's an implementation of that. So now let me run this, and you can see here's our x and y values. Okay, so what we're going to do next is we're going to define our x and our y. Basically, we're just taking each of these separate columns here. So essentially, we've got one input feature, x, and we're trying to predict what the y is. Here's where we actually create our model, linear regression, from the scikit-learn, and then fit is going to do the training. It's going to say, here's our training data. So remember, we just looked at the formula, so it's going to find what are those coefficients and the bias values that fit our data. And we're then going to, in order to illustrate and show what we've done, we're going to draw that prediction line. And so here we're going to xfit is just taking a set of values from numbers from 0 to 14. Actually, it's going to divide it up into 100 chunks just to make a bunch of predictions so we can draw our prediction line. And then this is some code using matplotlib, which is a graphics library in Python, which is going to plot our results. So let's look at what we predicted here. Okay, so you can see our data points are here, and the blue line is our linear regression model. So the blue line is what we are predicting. And you can see the distance from the blue line is actually our error rate. And here, so remember, we just have one input feature. So its coefficient or weight is minus 0.49. And the bias here is 10.4. So you end up with really a function for a line. And again, this is a simple example, so we can plot it in 2 dimensions. This code here is going to plot our data, but it's also going to draw the error line. So here you can see the dashed line is showing you what the actual error is on each of these points. So remember, we're predicting the y value, the vertical axis, and so that's why the error is shown as a vertical line between our data point and our prediction line. And we looked at some error metrics previously. So you can see here our mean squared error is 1.29 and our mean absolute error is close to 1. So that's essentially how much we're going to be off by on our predictions. We're going to talk more about why we use the squared error later on, but certainly either squaring or absolute. Really, we're looking for the magnitude. So from this perspective, how far off we are, whether we were above or below, from an aggregate perspective, we're not worried about. And we can see our R-squared score is 0.69. So what do we make? How do we interpret that? So here is kind of a quick read on how you can make sense of that. So anything over 0.9 would be considered an excellent fit, meaning you're really explaining all of this variance in the model and taking into account how all of the features fit into that prediction. So we're at 0.69, so we're right at the top end of moderate fit, but if you get values below 0.5, you're probably going to want to certainly look at different modeling techniques. Something I want to point out about linear regression, you can add more. We looked at an example with just one input feature. You can look at any arbitrary dimension as we saw in the formula. But I just want to point out that as you add more features, you still only end up with a straight line prediction. Why is that? Because when you add two vectors together, here's what happens. So I've shown here vector A in blue and then vector B in red. So vector A represents a feature that has a strong positive influence on our prediction. As you increase feature A, you get a large increase in the output value. Whereas feature B actually has an inverse, so as it increases, you get about an equal reduction in the output value. Now, when you add those vectors together, you get the green arrow. So essentially, you're still just getting a straight line prediction, but they're kind of balancing each other out. So just keep that in mind. And that is in fact one of the disadvantages of linear regression, is that many sets of data, relationships in the world are not purely linear. So linear regression, it is simple to understand and you can interpret it very well. We can look at those coefficients or weights and understand what effect does each of the input features have on what our model is going to say about it. But it's often not going to fit our data very well. It may in local points, but overall, you're going to see nonlinear relationships oftentimes. So it's not going to be, it's not going to be the most effective model in a number of cases. But it's a great place to start, and it's a great place to understand how these things work. Now, I should also point out that when we look at the straight line prediction, the way that it actually finds the best fit is it's minimizing the error. Remember we saw the error between the different points? It's going to minimize the square of all those distances. And whatever line does that, that's what the prediction is that we're going to end up with. Now, a related model is logistic regression. So in this case, we were predicting a continuous output, a continuous number. But think about a classification problem like our spam versus not spam. In that case, we just want to know, is it class A or B? It is logistic regression is only binary. It's going to handle only two choices. So in this case, what it's going to do is it's still going to draw a straight line based on that kind of linear relationship. But instead of trying to predict a point on the line, it's going to look at, does your data fall on one side or the other? What I've done here is I've added a few more data points. Remember we had that table with the 3 emails. I've added a few more fictitious data points, and I created a logistic regression model from that. So here you can see the red data points in the lower left corner are not spam, and the blue in the upper right corner are spam. So what did the logistic regression model do? Well, it found what it thought was a good fit, this linear black line in the middle that is separating our two classes. So in a classification problem, we're going to take the input features, plot that data point, and see what side of the line is it on. And by doing that, we'll know what is the classification of it. Is it spam or not? Another important thing is that you can look at and see some of the data points are closer to the line than others. And that affects the confidence level. So the closer it is to that dividing line, now we have a little less confidence in our prediction. Whereas if a data point is squarely in this lower left corner, we're very confident, no, this is not spam. If it's way up here in the upper right, if it's got a lot of spam keywords, many links, questionable links and attachments, we're very confident that it's spam. But you can see with the shading in the diagram here how the probability changes. And so this one more aspect in order for a machine learning model to accomplish that, and that is the concept of where in neural networks are called activation functions, but we use them here in logistic regression to convert this all to a probability. Probability is a value between 0 and 1. So we use sigmoid function to do that. So what is the sigmoid function? Well, you can see it here. You've got your input value x. So basically we're going to run our linear regression model. We're going to get some value, and then we can run it through this. So you can see on this plot below what it actually does is it takes a number in any, from negative infinity to positive infinity. It takes any number and it squashes it to a value between 0 and 1. And so why is that helpful? Again, because 0 is, we're sure that it's one class. 1 is we're positive that it's the other class. In the middle, it's like 50-50, we're not sure. And so you can see this curve here, most of the variation occurs close to 0. And so the models will learn to calculate values that are close to that. Remember, we used to have that bias term. So when that's included, that will shift in order so that we get these probabilities correct and we start making accurate predictions with our models. So that was an introduction to machine learning models. In the next video, we're going to dive into some more advanced models, but we're going to keep building on these concepts that we learned here. I'll see you then.